Okay, so this is failure is a four-letter word. This is joint research with myself, Andreas Zeller, at Saarland University, together with Thomas Zimmermann and Chris Bird of Microsoft Research. This research is concerned about software failures, as so much research is. We have the classical problem of trying to build software that's perfect, and we have a couple of little cracks in there, which we want to find out and which we want to fix. There's many examples of such software failures. I will not name them over here. But however, what we try to do is we try to understand how such failures came to be. For this, we look at the history of actual software projects. You know that Microsoft has done a great effort in this area. Unfortunately, I can't publish these many of the very exciting results that people have there. But this is one of our own stuff. This is, for instance, this is actually Firefox you see here. And the Firefox are the classes and packages of Firefox. And we colored these packages with respect to the number of security bugs that had been found in the particular places. Down here, for instance, this red corner is actually JavaScript. This is a JavaScript interpreter. And this is actually the area of Firefox where the most security bugs have been found and fixed. We also have here this red square up here. This is in the layout base. This is related to cross-scripting vulnerabilities. Over here we have the document object model, another source for security-related errors. And this is information we can today extract from existing software archives. We can map them, we can show them to people, and we can have people come up with the appropriate actions for that. The question, however, is, as we already have seen, what is the action that we're supposed to take from here? And there's been a plethora of work in the past years that has tried to relate these defect distributions to individual features of the product or the process. For instance, you can go and relate failures to the ability of your programmers, to their experience, for instance. However, in contrast to common belief, what you'll find is actually the smarter and the more experienced your programmers are, the higher the individual bug density. One of the findings we had in Eclipse, for instance, was that Eric Gummer is among the top 3 people whose code has the high defect density in Eclipse, simply because he gets tasks that nobody else can do. Another object of which failure causes can be related to is your specific style of management or the way your team is being built. Obviously, there's various ways to organize teams. At Microsoft, Vic Basili, among others, has found out that if you have a team that's composed out of many different groups coming from different backgrounds, and all of them working together on a piece of software, where no individual takes real responsibility, these are actually pieces of code which have a higher defect density. And of course, then there's all the product features such as metrics, general complexity. I mean, we were working on complex pieces of software, and the complexity keeps on growing and growing, and we have to deal with that at some point, and it's obvious that there should be a relationship to defect density. The problem we see with this is, with this multitude of approaches you have there, there's so many things, there's simply so many things you can correlate to defects. And the question is, for me, if I were a manager, what would I do? What am I supposed to do? And these consequences don't come cheap. We call this the cost of consequence. If I go and say, I want to reduce complexity in my code, this is an investment. If I need to reorganize my teams, that's an investment just as well. If I have to go and send all my folks to programmer training for a couple of months, yes, these are real costs, and I want to, and I need to know which of these actually to choose. And well, what this leads to is procrastination, because I have so many choices, I prefer doing nothing at all. And this is bad for our community. What I'm suggesting in this talk is we should go back to basics, to the very to the very beginning, to the very core elements that initially make up programming. And what do I mean by such basics? What I mean is programmer actions that take place wherever code is being written. No matter what project, no matter how your team is organized, no matter whether you're an individual or whether you're talking about big teams. And these basic actions, begin with keystrokes. Simple keystrokes as they occur. Well, this is how everybody writes code. Well, we have a couple of people who do model-driven development days, rather point and click, but you can assume that initially it's simply typing, and the typing creates the characters that make up the code at the very end. And if we look at this, if we take this view of source code, what we get is essentially a view in which we get rid of all possible abstractions. Because looking at a piece of code simply as by the letters it constitutes of is possibly the lowest. It's possibly the lowest layer of abstraction you can look at it. You could look at it as a sequence of bits if you wish to, but this is no longer a layer at which we humans typically consider code. So, what we've been doing in this work is we have looked at the distribution of individual characters in files, and built a couple of hypotheses on that. First hypothesis is we can actually go and predict defects from these basic programmer actions. Second hypothesis is we can come up and isolate programmer actions that are actually prone to creating defects. And number three is we can prevent these defects by restricting the actions of programmers. Let me start with the first hypothesis. So, are we actually able to predict defects from programmer actions? For this purpose, we did something pretty popular these days. We simply looked at a popular bug data set. This was actually prepared by two of us, Tom Zimmermann and myself, at Promise 2007, hence the link here to this conference. This consists of 3 releases of Eclipse, varying between 6,700 and 10,500 files, are consisting of 44 million characters up to 76 million characters in these files. And for every single file in this bug data set is listed whether the file would have had a defect or not. And this number of defect-prone files typically is between 11% for Eclipse 2.1 and 15% for Eclipse 3.0. This is the basis on which we conducted our investigation. First thing we looked at the distribution of characters, because, of course, we want to avoid specific bias. We wanted to check whether the distribution of characters would be in some way shifted or in some way abnormal. What you can clearly see here, these are the ASCII codes. There's a clear trend towards printable characters, which is not so much surprising. Actually, the most frequent character is the space character. Over here, we have carriage return and line feed. These are the uppercase letters, and these are the lowercase letters. And you can see that lowercase letters, this is Java source code, I should say. Lowercase letters are by far the most prominent ones. The most prominent letter in here is actually E. You can actually check that the distribution of letters in the Eclipse source code is pretty closely matches the distribution of letters in arbitrary English text, which leads us to the belief that we could actually apply this to arbitrary text, but I'll come to this later. So the question is, if you look at an individual file and look at its individual distribution of characters, can you use this as a way to predict whether a file is going to be defect-prone or not? It turns out, indeed, you can. What we did is we trained a regression model on these 3 Eclipse releases on the distribution of characters and whether they would be correlated with defects or not. And then we checked, and then we used the very same model to predict. Whether a file would be defect-prone or not. What we found was that we gained a precision that was on average 55%, meaning that more than every second file predicted as being defect-prone actually was defect-prone. And this, if you consider that there's just 15% of files that actually are defect-prone, that's actually a pretty good result. And we did this across all the 3 releases. We made the appropriate predictions in here. You'll also find that the best results are actually achieved if you use the same training set and the same test set. Meaning that you use Eclipse 2.0 both to predict and to test. And this is something we found very exciting, because this is, of course, the most prominent and the most useful usage of these data sets, because I am working right now in Eclipse 4.0, and if I can predict something right out of Eclipse 4.0, this is the data set that's most relevant for me. So this particular diagonal, this is something we were very excited about. Also something you don't see too often. We also looked in terms of recall. In terms of recall, essentially we have a bug-finding tool, and in terms of recall, none of the bug-finding tools is especially prominent. There's still many defect-prone files which we can't predict, but overall we were able to achieve a decent recall of 20%, which is on par with other prediction methods. Other prediction methods, which I should say, are usually way more elaborate and use lots and lots of abstractions and constructs. So this is regarding our first hypothesis. Can we predict defects from programmer actions? Yes, we can. No problem with that. The second thing, of course, is now that we know that we can predict something, what is it actually that creates these defects? And so we went and looked for actual causes in there, not only for correlation. And what we did is we checked the individual correlations of characters with defect proneness. Meaning that, and this is the actual result. Just looking at the lowercase letters in here. This is the correlation between the abundance, the number of individual characters in there, as well as the number of defects per file. And now you look at the individual characters, you see there's a huge difference in here. There's characters which are, there's characters like I, yes, because there's a high correlation, others have a far lower correlation. And now you look at the top correlations in here. And the top correlations, are the letters I, R, O, and P. These are the actions that correlate most with defects in files. We were very excited about this, and we named we therefore took these four letters, the four letters of failures, and named this IROP, the IROP principle. IROP is actually also airline slang for irregular operation, which makes this an even more catchy meme. And we think it's important to have a catchy meme in there rather to have long, complicated titles. Just name it like this. Now we know these are the four letters. This is the four-letter word that failure is made of. And yep, indeed, we can go and find out which actions are the actions that are most correlated with defects. Third point is, can we actually go and use these insights to prevent defects in the future? And for this purpose, we started a couple of experiments with interns at Microsoft. I was there for 2 months, so we had plenty of time. And first thing we did is we went and color-coded the individual letters on a keyboard. It basically looked like this. So you can see here the color coding simply means the correlation of the individual letters. You see that numbers, for instance, up here have a low correlation, but again, it's the particular letters that count most. Actually, I should also point out that the return key, meaning line feed character, also heavily correlates with the number of defects in a file. And we thought that, well, maybe it's a good idea to make this explicit to programmers. But then we found out that most programmers at Microsoft actually are touch typists. They never look at the keyboard. So we said, okay, since they never look at the keyboard, we're going to make this a bit more drastic. And so we designed a special keyboard on which the letters that would lead to failure were simply taken away. And so you can see IROP is missing. We originally also, this is something that's only briefly addressed in the paper, we also considered removing the enter key, but then it turned out that the number of defects per line dramatically increased, so we put this back in. So, and this is what we gave to the interns at Microsoft to work with. So of course, this is a drastic measure, and I'd like to relate to some of the experience we had. First thing was, these letters of failure occur anywhere in code. They also occur, so it's not only in identifiers, it's also in keywords. So we actually had to come up with appropriate renamings. Of course, we're Microsoft, we can do that. So we came up with appropriate renamings such that the code would no longer contain these characters. And these renamings, the good thing about these renamings is you set up an automatic renaming tool. The good thing is this is 100% semantics preserving, meaning that all these automatic changes will not have any bad impact on your code whatsoever. It's just a matter of getting used to the new keywords. That's all. But afterwards you can work as you did before. Actually, when our interns realized that they would now be able to avoid these failure sources, their habits changed. I could talk about the 7 most important habits of Microsoft interns, but one of the habits they quickly found out was, well, they didn't want to type these keys anymore. So they used this even in their daily communication. They avoided these letters right from the start. We can shun these set majuscules. These are the 4 letters. And the text change just as well. The text change just as well as antecedentally. Let us just ban them. This is what one of our interns sent us, and obviously this was typed on what we call now the IROP keyboard. So this is our last part. Can we prevent defects by restricting programmer actions? And indeed, yes, we can. So this research, we posted a picture of the IROP keyboard well before this conference on Facebook and Twitter, and we got, as well as from within Microsoft, we got plenty of questions about this research. I'd like to address some of the comments we get. The first question, of course, is external validity. I mean, how many items did you actually look at, and can we generalize from them? And the thing is, I'd really like to stress this. We looked at more than 177 million individual characters and thousands of defects. This is actually something that brings standard statistical packages like R to its knees, because the base you're looking at is so huge. And I think, yeah, you can always come up with more characters and come up with more like this, but at some point, I think enough is enough, and numbers as big as these is something you can't really mess with. So this is one of the largest studies ever, and we're very happy about that. Second thing is, are the correlations significant? Yes. They're all statistically significant. We pointed out those who weren't. All those I've shown in here, including the lowercase, but all of these are statistically significant. We have a couple of insignificant correlations. These are typical non-printable characters which make it to the Eclipse source code, but where there's a low number. But all of this is significant. This is in respect to internal validity. The third point is, of course, validity. Construct validity. Does our construct make sense? And here, the interesting thing is, which construct? Because we're just looking at the characters. There is no construct from our side involved. There's no abstraction from our side involved, which could mess in any way with the findings we got. And this is, and of course, well, code is input as characters. This is a well-known fact. There simply is nothing you can question about this. So this is our comment to the possible threats to validity. Future work. Yep, plenty of things to do. First is we're still working on our tool for automatic renamings. We're making this more semantics aware, where I know how popular ontologies are in software engineering. We're using such ontologies for good renamings. A promise, for instance, is about the worst word you can think of for a conference, I should say. We're renaming this to engagement. Eclipse, in other cases, we simply remove the letters. This just takes a bit of use. It just takes a moment to look at. Another thing, of course, is despite us intentionally negating abstractions, we're looking at abstractions. We're looking at ways to explain this phenomenon. And one thing that we found is, and this may be one of the keys to this phenomenon, is that quite a number of words that we find as negative in our work, say failure, mistake, error, problem, bug report, all contain the 4 letters of failure. Whereas positive words like fame and success do not. maybe it is the case that when you're already, you intuitively associate these letters with negative feelings, and therefore while you're typing them, you have these negative feelings which you don't want to see them, you don't really check what you're typing, and this is one of the possibilities how these letters would eventually cause a higher failure rate. And finally, of course, generalization. We're currently looking at a big bunch of Russian source code, and it turns out that they're just as well as in our Western-speaking countries. We find the same principles, and we find similar letters that correlate with failure. With that, failure is a four-letter word. I am happy to take. I'm happy to take one or two questions. Yes, this is quick, Stefan.
This is all pretty nice, but I'm just wondering. You just use Java code. Is that transferable to other kinds of programming languages?
Yeah, that's a real nice thing. You know, if you look at tokens, or if you look at whatever abstractions you look at, if you take object-oriented abstractions, you always rely on these abstractions. Here we look just at the basic things, and we haven't done this yet, but in principle this works for Fortran, this works for COBOL, this works for Mail, this works for anything that comes in characters. And I think this makes this a very general and very generalizable approach, which actually makes it superior to lots of other work, which is typically specialized on a specific version of a language, for instance.
We should actually also prevent inputting those characters as ASCII code.
You mean Yeah, I understand. Yeah, okay. Indeed, in daily life, if you have an IROP keyboard, it's not so easy. In particular, if you work within Microsoft, typing at Microsoft.com, for instance, can become quite a burden. Actually, but all tech companies have IROP in them, so almost all of them. We should check that. But what we found was that so indeed, maybe I should point this out. Of course, the interns were still able to enter these characters by pressing Alt and entering the appropriate octal code. This is how this works on Microsoft keyboards. But you know that every time they enter one of these characters, it becomes a conscious act. So they are aware of the problem. They are aware of the problem, and they say, okay, I am now going to do this dangerous thing, and I'm entering this character, and this means by definition they're spending more time on it. They have more ways to look at them, and they are much more aware of the work they're actually doing, which actually, and this is one thing that's just recently found out. Turns out that now code that still contains IROP is actually better than old code because people are aware, oh, I need to use an I over here. Let me take extra care that it all works. So this is one of the interesting side effects we're seeing today. Yes.
So is the IROP keyboard real stuff?
The IROP?
Is that a real keyboard?
This is a real keyboard, sure. Sometimes
have you got a real prototype?
No. This was a special keyboard which was manufactured for us. What we wanted to have.
That's right. Which company?
But what you actually can do, this is super simple. All it takes is a screwdriver. You take away the individual characters. So building an IROP keyboard on your own is a super simple thing. So it's not really difficult. Tom, you're there at the back.
Yeah, I just wondered, did you consider instead of removing the keys, why not leave the keys but you wire some electric current? So anytime you type, this would be a more object lesson for the program.
Yeah. So the idea would be to wire little electric, to give programmers little electric shocks regarding on these letters. Yeah. There's actually when you're in Microsoft, I'm sure this is within the range of things, but there's a small number of programmers who actually are in unions, for instance, and you know how the American legislative system works. We were afraid that some would sue us, and therefore just making this a no option rather than punishing them in some ways was not directly in our industry. Yep.
I was thinking so now, right now the letters from the keyboard are removed, but as a programmer programs more, maybe it just becomes used to using those. I mean, if he wants to use I or something, maybe he becomes used to it, and now he's no more conscious of that he's typing this, and then he becomes again used to it. So then.
Yeah, the thing is, if you remove these characters, And of course, yeah, there's going to be other characters, and in the end, you'll again be able to figure out which characters are there. But this is something we see every day in programming languages. I mean, consider the first programming languages where there was no decent typing, for instance. People made lots of typing errors. Programming languages evolved, now have checks for typing. And as programming language, the evolution of programming languages can be seen as a way to where one error source after another one is removed. And this is precisely what we do with these keys. We remove these error sources. Yes, there's other error sources remaining, but for us, this is just part of natural evolution. So this is the vision we're going with. Okay, I'll skip things. I'll skip things here because you may obviously have realized that very little of this makes any sense. And I apologize if anyone had missed the parody in there. You may wonder, well, why do we come up with such ridiculous stuff? Well, for one thing, it's fun, but we actually wanted to point out a couple of observations we've seen in the past years. The first thing is correlation versus causation. With the abundance of publicly available data sets, what we frequently see is that people come along and actually do it the very same way that we did. They download a data set, find a correlation somewhere in this single data set, and come up, oh, we found a correlation between such and such. Isn't that great? Yeah, sure, that's nice to have, but the question is, does this generalize? Does this make any other sense? And in particular, can you explain that there is a causation in there, which we actually never, which even this IROP work, which is the causation thing we came up with is, from a scientific point, not too solid. Next thing is, this is another observation. Machine learning will work no matter what you feed in there. If you feed, you can feed the number. You can feed the number of individual characters in there. You can feed the number of you can feed character distributions in there. There's plenty of predictions that will yield good results. So the fact that simply we trained a model on this set and we came up with this prediction, and lo and behold, it works. Yes, it works. It would actually be a surprise if it would not work these days. This is another observation. There's many ways to predict things. They all work, and this is, of course, there's things that work better than others, which is an interesting scientific problem. But generally, the fact that prediction works is no longer much of a surprise. Cherry picking. In the paper, we actually write, after a set of initial experiments, we focused on the Eclipse 3.0 release because it would yield the best results. Okay, this is verbatim in there. This was not exactly verbatim copied from another paper, but there's papers in the wild that say, for our evaluation, we selected 5 programs, period. No word on how these were selected, which criteria whatsoever. And lo and behold, we find excellent results on all 5 of them. This is the average. See, the thing is, if you select 5 programs and then come up with first you select 5 programs without saying what it is, and then you come up with a concept like average, this is very doubtful. Actually, I remember contacting the author and asked him, did you never try this out on another program? No, never ever. Only on these 5. Because otherwise, we'd have to report it or something. Other details in here, look at how the scale is totally exaggerated. It's all from 0.31 and 0.35. If you make this a regular picture with a scale from 0 to 1, you'll find it's all flat, actually. So, because eventually it's the number of characters, and not the individual characters, that simply correlate with the number of bugs. Fixed causes, not symptoms. Again, coming up with something that's actionable in the end. Coming up with something where we can have a good consequence. Actionable findings. Certainly not looking at individual letters, because you can't remove these individual letters. You have to have people work in the same way as they did before. And while we're at it, I'd also like to point out our inspiration, which actually makes a great introduction into the dangers of statistics. This is from the XKCD comic, which is actually a nice read for anyone interested in science. So here we have a person who says jelly beans cause acne. Scientists investigate, and the investigation shows there's no correlation between jelly beans consumption and having acne. But then we look at the individual colors of jelly beans. So we found no link between purple jelly beans, no link between brown jelly beans, no link between pink jelly beans, all at a certain level of confidence, of course. The fun thing is if you do this repeatedly, 20 times, each with a confidence factor of 95%, you will always find one correlation between, say, green jelly beans and acne. Whop! Wonderful. And then, after you've done your 20 experiments, yeah, of course, the conclusion is green jelly beans linked to acne. This is 95% confidence. Wonderful. Totally love that. And this is actually what we did in our paper. We simply took these 4 letters and linked them to failures. So we wrote this paper specifically because we wanted to see how much of bad statistics we could possibly put into a paper and still sound somewhat credible, at least in the beginning. One of our inspiration also was How to Lie with Statistics, which is actually precisely what we did. The paper is available for download, obviously, right here at this conference. We also set up a website, which is mentioned in the paper, where you can also download the original Word file with which this is produced. So you can actually go and say, take away the authors or take away the parody part in here. Use this in class and have your students dig through the paper and find out why all of this is wrong and how to do this in a better style. This is what we eventually hope to achieve. That IROP is going to become a meme of bad research, and by packaging this in a hopefully fun and easy to read way, we can teach people more about statistics than coming up with long lists of standard recommendations that we read, we nod, it's fine. But this way we can point out a couple of real issues, possible issues as well as real issues. With that, I'd like to close. This is where you can download everything. We also have put together the R scripts and the data which we used. All of this is available. All the findings are real. Actually, I should point this out, except for the keyboard, which never existed, of course, which is deliberately badly photoshopped, such they can notice it. But everything else is here at your convenience. Thank you very much for your attention. And I'm happy to take questions again. Okay.
So maybe another warning to models could be the fact that, in this model, you're assuming that letters are independent events. And maybe yes. a lot of times this also happens in prediction models, so this can again be a warning.
These letters are all intercorrelated with each other in reality. The individual letter doesn't count that much. What counts is the length of the file. And the length of the file can be easily correlated to the number of bugs in there, which is not that surprising if you consider that there's some average bug density. Then the longer a file is, the more bugs it will have. This is what we found out in Eclipse. This is what we found in Eclipse, which was not much of a surprise. But then we looked at the individual letters in order to put some spice into there. Yes. 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 There's, if you, we actually did a real study where we correlated defects in Eclipse not to the usage of individual letters, but to the use of individual tokens. This was an exploratory study. And there we found that there was a little specific correlations between individual tokens. But what we found at this point, and this was very interesting, was that the relationships to other modules, for instance, were very interesting. So what you imported determined very much the likelihood of failures. We also used this for this Firefox study, and this this worked very well. So there are indeed real sources of failures, and most particular the length of the file, the number of changes, the number of developers associated with it, as well as the general domain in which your file is located. Pretty much obviously there's domains, say like user interfaces, where errors become much more visible than say compiler internals, where any errors take many steps to actually manifest themselves.
Any other questions? So once again, thank you.
Thank you.